What's up, YouTube? In this video, I'm going to show you an IoT vulnerability that I think anyone can find. And by anyone, I don't just mean any IoT hacker. I mean, if you're watching this video right now, then I think I can show you how to find this vulnerability. And not only are we going to cover all of the details about this vulnerability, but I'm actually going to walk you through the specific steps that I use to actually go out and hunt for these vulnerabilities. Before we dive into the details of this vulnerability, let's hop over to the TCM blog for a free resource that you're going to want to check out if you want to follow along with the steps in this video. This resource is a 4-part blog series that I put together on how to get started with IoT and hardware hacking. And it walks through all the things like the equipment that you'll need to buy and how to actually find some of your first vulnerabilities. And one of those is the one that we're going to take a look at in this video here. So I'll drop a link to this whole series down below because some of the setup steps I'm going to skip in this video, but they are very well detailed in this blog. Now, let's talk about the vulnerability that we're going to be hunting for, and that is command injection. This is an extremely impactful vulnerability because it allows for remote code execution. This vulnerability is not exclusive to IoT devices. However, in my opinion, it is much more prevalent due to the limited amount of funding for R&D to go and develop these IoT devices. If you're not familiar with command injection, this is when an application builds and executes system commands that actually use unsanitized or unvalidated user input. So to break this down, this essentially means that an attacker could craft an input that contains a command that is then going to actually be passed down to the system to be run from the application. This is kind of just like allowing an attacker to be able to sit at a terminal and type in a command. At this point, we've got enough details to actually dive in and start hunting for our own command injection vulnerability and taking a look at the methodology that I use and also suggest beginners use to make it super easy to hunt for and find these vulnerabilities. In today's video, we're going to be taking a look at some custom firmware that I have written that has a command injection vulnerability in it, just to make it a little bit easier to go out and identify this. However, the steps and methodology that I'm going to show for this firmware will also work for most commercial off-the-shelf IoT devices as well. So let's quickly take a look at where you can grab that firmware. It is in the GitHub repo for the dumb thing firmware, which is what this device and firmware is called. I'll drop a link down to it below. So if you actually go in and then go to the releases, you can actually just go here and download it. So at this point now, let's hop over to our virtual machine and I'll walk you through the methodology. I'm going to be using a Kali virtual machine because it has the majority of the tools we already need. However, you can really use any Linux distribution you are interested in using. The first thing we'll want to do is get our hands on a copy of the firmware. So one of the unique things about security research on IoT devices is the ability to usually easily get a copy of the firmware that can be looked at. And this allows us to look at the device from both the outside and also the inside. So with some reverse engineering, we can get pretty close to looking at the source code for the things like the binaries and scripts inside of the device. So if you compare this to something like a web app where you can only look from the outside, this makes it a lot easier to actually go and hunt for vulnerabilities. In this demo, we'll just be looking at this example firmware, which we can get by going to the releases page here. And then if we just scroll down to the assets and right click here, we can just go copy link and then download this directly with wget. So if you're working with a commercial IoT device, then of course you're going to need to either go out and do some OSINT on the web and find where you can download a copy of the firmware, or alternatively read it off of the storage of the device itself. We're not going to cover that in this video. However, later on, I'll talk about some resources of where you can go and learn how to do this yourself if you want to do this on a commercial device. So I'll just pop open my terminal here, and then I'll use wget to download this. So we'll just let it download here. And then if we actually just list this out now, we've just got this zip file. So we can unzip it with unzip command. And then if we list it out now, you'll notice we have a .img file. So because this firmware is designed to be loaded onto a Raspberry Pi Zero, it is in this .img, so it can easily be loaded onto a micro SD card. However, for commercial IoT devices, you're usually going to see this in a .bin format. That's the most common. Now, with the .img for an SD card, we could just actually mount this and then take a look at the contents of the firmware that way. However, if it's in other formats like the common .bin, then it's not as easy to actually access and see what is in that firmware. Luckily, there is an open source tool that is very good at picking apart the different sections of firmware and allowing us to then extract those and take a look at the inside of them. And that tool is called Binwalk. So we're going to use Binwalk on this .img file, even though we can mount it, because this is the process you would use for a commercial set of firmware from a device. So let's clear this away again here. And then if we run Binwalk without any other extra arguments other than the firmware file that we want to take a look at, it will go and see if it can identify different portions of it. So we'll do that here with the .img. And when we let this run through here, you'll see we're getting all of these different sections. So on the left column here, it's giving us the addresses here, and then it's on the rightmost one, it's identifying what it thinks the different sections are. And keep in mind, it doesn't always get these right, but usually for the important stuff, it can. And if you take a look down here at the bottom, we actually get a Linux kernel here. So this device is running embedded Linux. And then we also get here, down here, a Linux ext file system. So generally, this is going to be the main thing that you are going after when you are doing IoT hacking on an embedded Linux device, and that is what is called the root file system, because this contains all of the things like the binaries, the scripts, the configuration files that actually make the device do what it is designed to do, and those are where most of the vulnerabilities in that device are going to be present. So now that we've identified this, what we can do is clear this out, and then now we can run Binwalk with the extract option to go ahead and actually go and extract all of these sections that it can out so that we can take a look at them. To do that, we'll go Binwalk again, but this time we will pass in the -M and -E, and then we can pass in the name of the firmware as well. Again, this img file. So before I run that, just to quickly cover what these options are doing. So the -M is telling Binwalk to actually recursively extract. So if it extracts something and then it finds another format that's not the end format of a file, it will keep extracting. So the -M is for Matryoshka, which is like those Russian dolls where they keep stacking. That's what that means. It's to recursively extract. And then the E argument just tells Binwalk to actually perform the extract and not just list out the sections it finds. So we can let this run again here, and then it's going to extract everything that it's actually able to for us. This will take just a little bit longer for it to do that extraction. So we'll let it run through here. Mine's done. So if we just actually now list this out here, you'll notice we have the .extracted, which contains everything that it was able to extract, and it is a directory, so we can navigate into that directory here. And then if we list out the contents now, we actually get some more details about what has been extracted. And the default, if Binwalk is not able to identify the name of it, is it will give the actual address location. So that's why we have these addresses here. The thing that we're most interested again is the root file system, which is ext-root. In this example, it's using an ext file system. However, you'll commonly see a lot of other different unique file systems like squashfs or jffs2 being used. And Binwalk can handle extracting those usually as well. So let's navigate into this root file system here. and let's list out the contents here just of the top of the root file system. And you'll notice, if you are familiar with regular desktop Linux, you are seeing a lot of the same folders and structure that you would see, and that is because this device is running embedded Linux. Nowadays, a lot of IoT devices are running embedded Linux, and if you're getting started with IoT hacking, then I very strongly recommend you pick out an embedded Linux device. It makes it a lot easier. If you're looking for a commercial device and you want to make sure it has embedded Linux, then my suggestion is to pick a cheap router or smart camera, as these almost always are running embedded Linux. The other alternative to embedded Linux is that systems may run something like an RTOS, which is a real-time operating system, or just a custom bare metal application. And these are a little bit more complex to be able to reverse engineer, so I would leave those for later on. Once you've got the root file system opened up, what I suggest you do, and what I usually do, is perform some manual enumeration. When you're getting started and learning, it's probably best to actually do a full manual enumeration of the whole root file system and see what you can find. In this video, I'm not going to do that, but I am going to show some common points of interest or places I always look. So let's actually kick things off by taking a look at the bin folder. So we'll go cd bin here. And then if we list out the contents, we can see that you'll see a lot of the common Linux utilities or binaries you would expect to see. So one thing to point out if you're not familiar with embedded Linux is this BusyBox binary. So usually in embedded Linux, you will see BusyBox, which is a tool or binary that actually combines the majority of those standard Linux utilities and binaries into one large binary. And what this does is it actually allows saving of a lot of space, because on embedded Linux, there is usually limited both memory and storage on the device. And this allows all those binaries and utilities to be shrunk into one smaller file. So what you'll actually see is that the majority of these other binaries and commands, they're actually just symlinks that allow you to directly call BusyBox without actually having to, pass in BusyBox and then all the arguments. So if you actually just go ls-l here, for example, you'll see that the size of most of these is very small. This is the size here. However, we've got bash here and then BusyBox, which are actually file sizes. So we can use this to our advantage as well, because what we're going to want to look for is mostly custom binaries. Usually you're not going to find vulnerabilities in the actual Linux utilities themselves. A lot of times, if those were going to be found, they already would have been through the open source community, or alternatively, we can just go look at the source code for those ourselves. So I'm not seeing anything in here that is of interest. It looks like it's mostly just those common Linux binaries here. So let's clear this out here and then go back up. And let's take a look now in the sbin folder. So we'll go into sbin here, and then we'll list this out with ls-l again, so we can get the same idea of the symlinks. And if you take a look now, we're seeing some that look like they may be custom. So we've got this controller here, which looks like it may be a custom binary, so potentially something of interest. And then the other one that's really sticking out to me here is that we have HTTPD. So it looks like this device is hosting a web server. This is something you'll commonly see on IoT devices to self-host a web server, and that will be the UI for users to be able to go in and make configuration changes to the device itself. So definitely something of note, and that we are going to look at further on. Before we do that, though, there is one other very important spot that I want to take a look at. So we'll clear this out, and then let's go back up to the root file system, and if we list it back out, and that is in the etc folder or etc folder. So this is where a lot of the configuration for the device is going to live. So we'll go cd into here. And now if we list this out, you'll notice we have a bunch of the configuration files. So I always like to take a look at these. Sometimes you'll find low-hanging fruit like API endpoints or keys or passwords in here. And then also of importance is all of the initialization scripts. So those are usually going to be in a folder called init.d. So if we actually go into that directory here, so we'll go init.d, and let's give ourselves some space and list this out. Inside of the init.d folder, we have all of the initialization scripts that are going to be run on startup of the device. So the way that it works in a BusyBox system with init is that it will actually call the RCS script first, and all of these are just shell scripts, so you can go ahead and cat them. So if you cat this out and read it, it's just going to be in plain readable text. So we'll cat RCS here, and then if you actually look at what this is doing, is the way that it works is it actually just then goes through and calls all of the other scripts that start with a capital S, and it does so in alphanumeric order. So I'll actually call them in the order that we see them all here. And what I recommend is actually go through and read through every single one of these scripts. So not only will they give you a lot of details just about what the device is doing and any custom binaries that are going to be called and set up, I also very frequently find vulnerabilities in here. So things like reaching out to interesting API endpoints, potentially hard coding keys or credentials, or even sometimes things like command injection or other specific vulnerabilities are in here. So let's take a look at maybe just one of them here to see how they're working. So we'll clear this out here, and then if we list this back, maybe let's take a look at how DHCP is working here. So we'll go cat S41, and it is DH here. And we can actually just take a look and see that it is bash here setting up the DHCPD. So interestingly, we can see, for example, where the config file is. So this isn't going to be the focus of this lesson though, but I did want to show you should always look here. So let's actually just clear this out now, and we'll take a look now at how to find that command injection in the binary we have been hunting for. Since we identified there's most likely a web server running on this device from the presence of the HTTPD binary that we found in the firmware, the next thing I'm going to do is actually interact with the live device that I have here in my lab, and then see if we can navigate to the web server.
Are you looking to up your cybersecurity skills in 2025? The TCM Security Academy has you covered with our affordable and high-quality courses. In addition to the 25+ courses, we also offer certifications that feature hands-on labs specifically built to test the skills you need to succeed in cybersecurity jobs. No multiple choice questions guaranteed. Explore certification and career pathways at certifications.tcm-sec.com.
So if you want to set up your own device on a Raspberry Pi like I have, then make sure to check out the blog that I linked before, because it has all of the detailed steps about how to actually set up this device with the firmware and get it connected to your network. Now, we could always run an Nmap scan on the device as well to see what ports are open, and of course we would find the web server through that way as well. And if you're actually testing a device, then I would highly encourage you to run Nmap, but we're just going to take a straight shot there and head over to its web interface. So to get there, we will just go http:// and the IP address of the device. So for me, that's 192.168.50.126 right now. We'll head over, and then you'll notice we're prompted with a sign-in portal. So one of the most common, I believe it's at the top of the IoT OWASP top 10 list, is very weak default credentials that are not required to be changed. You'll see this on a lot of IoT devices. So one of the most common ones is just admin. So we'll give that a shot on this device, and that will get us in. And now we've got a very basic web portal here that allows us to perform some control here. So we can turn the device on and off, we can set the system time, and we can do some schedules for when the device is going to turn on and off. So essentially that's all this device does. That's why it is the dumb thing. It can just turn a light on and off and allow for scheduling. At this point, we could treat this like a regular web application penetration test or bug bounty hunting and start using some tools, scanning and fuzzing and maybe directory busting to see if we can identify any vulnerabilities in this, and maybe we would find some through that method. However, The method that I like to employ takes advantage of the fact that we actually have access to the firmware in the backend, and also for this one, a live device. So what I'm going to do is actually connect to the UART of this device, and then we'll take a look at some of its logging while we interact with the web browser. And if you're not familiar with what UART is or how to connect to it or the tools that you need, again, there is an entire blog in that blog series just about UART that you can check out that has very detailed instructions and descriptions in it. So make sure to check that out if you need a refresher. So what I like to do then is hop over to the terminal, and I've already got my UART session opened up here, and we can see the logs are already streaming in. So what I'll do usually is take a look at both the UART and the actual browser itself at the same time. And that way we can actually see if there's any logs being triggered while we are actually interacting with the device. And then this can help us trace back our interactions with the device to the underlying code. And this makes it really easy then to hunt for potential injection areas and be able to look at the direct code that is actually the result of us doing something on the device. So for example, if we start by turning on the status, you can actually see we get a bunch of different logs streaming through. So we have this on command received, and we're updating a config parameter. We have this light control that the light turned on, and then if we turn it off, we'll see some more streaming through. And this actual logging details in the UART is common to what I see on a lot of commercial devices, where we actually have some details in these square brackets about either potentially the binary or sometimes the actual function from a library file that is actually being used. And we can use this in conjunction with the actual text here to then go back and hunt through the actual firmware for what is actually, writing this logging message and also controlling the device when we interact with it. So let's take a look here at this set system time as well. So right now we have the time set here. It is the current time that it got, and we'll go ahead and actually manually update this. So maybe let's put it to tomorrow, and then we'll set a time here. So we'll go 14, maybe we'll go, 10 p.m. So we'll hit update here, and then you'll notice we get a bunch of logging come through here as well. So we get the details about checking the schedule, setting the date time, and up here at the top, actually, you'll notice I see something that's quite interesting. We get the set system time, and it says formatted set date commands, and then it looks like it's actually calling a script and passing in a parameter that we are actually in control of as the attacker, which is that time that we set. So when I see this, this is very interesting to me, and something that I always look for is to see if any of the parameters that I'm passing in look like they're actually being passed to a command. And in this example, it does. And this is something that actually happens quite commonly in IoT devices, because a lot of times it is much easier for developers to actually use already pre-built binaries and utilities in Linux to do things like change the time, or if it's a router, to change some of the details about the SSID. So those will actually be passed down to a system command, which then calls those binaries. And then, of course, if those inputs aren't properly being validated, then a lot of times we can perform command injection. So now let's actually take a look at how we can find the underlying binary or library that actually has this code so we can reverse engineer it. Once I have a log message from the UART that I want to find the underlying binary or library for, what I'll do is actually run strings on the firmware itself and then pipe the results of that out into grep to look for either a keyword or the function name or some part of the string so that I can find out what binaries or shared object files or libraries actually have that. So to do that, let's run strings here. And the important thing to remember is to use this -f option, because that's going to give us the file name, because we're going to be running this across all of the different files. And if we don't, then we won't know what file actually had the hit. And then we'll take a look at everything. So if we run star here, and then we'll pipe it into grep, and we're going to look for the name of that function, which was set system time.
And we'll run this here, and you'll notice we just got all these warnings that these are a directory. So unfortunately, strings can't do this recursively unless you write a quick script to do it. But another trick is I'll just keep going deeper manually. So if we just go and rerun this again, we can go star and then go /* here and then run this again. And you'll notice we actually get 2 hits here for this HTTPD where it's being used. So this is a great sign to see now in that binary for the web server. We have this function being called. So it might be tempting right now to go ahead and actually try and start reverse engineering this binary. But to save some time, what I like to do is I always like to make sure to check and see if that function is actually most likely being called from another library, which you'll very commonly see in IoT devices and not specifically in that binary itself. So one way to do that again is we can go one folder deeper with our strings, and we can take a look at then what we see if we keep going deeper and see if we see any libraries or shared object files that we have. So let's go one deeper. And now you'll notice we actually have in the lib folder this libdt, libdt being for library dumb thing, .so. So .so, this is a shared object file. So this is where other functions are going to be that can be called by all of the different binaries. So this is most likely where the underlying code then for this set system time function lives. So one of the things that I really like about this methodology of using the device and then looking at the logging details and then using strings and grep to identify where the underlying code is it saves us from this sort of needle in a haystack scenario that you can be in if you are not familiar with IoT hacking and where to actually look first. And now, from potentially dozens to it could be hundreds or thousands of different binaries and libraries on a device, we've actually easily identified one that we know takes user input. And now we can quickly go and take a look at that. So next up, we're going to launch up our trusty Ghidra and do some reverse engineering. So I'm going to start a new project here, a non-shared project, and I'll just call this dumb thing demo here. We'll click finish. And then what I'm going to do is we'll import the shared object file that we want to look at here. So we'll go file, and then we'll go import file here. And then I'm actually already here in the firmware that we've extracted. So that was in user/lib that we identified. Go here. And you'll notice how many shared object files there are here. So if we were actually just going to look at all of them, there is a lot to take a look at. But luckily, we know the one that we're looking for is that libdt.so. So if we take a look here through, we should be able to find it in alphabetical order. And there we go. So I'm going to select this file to import. It gives us some details about it. So for example, we know it's a ARM Little Indian. And then we'll click OK here. Allow it to import, get some more details about it now that it is imported. And then what we can do now is actually just double click on this. I'm going to allow it to analyze as well because it's going to make our analysis easier. So let that run through here. Just run through with all the default options here, hit analyze, and this sometimes take a minute or two to run through. Mine's done analyzing, and we can just skip this error message that we get here, click OK. And now we actually have the decompiled version of this binary that we can go ahead and read through. So again, we could start reading through all of this binary and trying to figure out what's going on. However, it's quite intimidating when you are first starting out. And luckily, we've already identified what appears to be the function name already, so we can just jump straight to that and start taking a look. So let's go into functions here on the left in the symbol tree. And if we actually just open this up, we can just jump straight to the different functions. So notice we have a bunch of interest here. So one that gets the current time for setting the schedule. And of course, we have that set system time that we were interested in. So if we just click on this, it will actually then just jump straight to where this set system time is actually going. And on the left here, we actually have the raw assembly here of it. And then on the right, we then have the decompilation view. So this is what I'm most interested in because this is a C representation of what is actually happening in that assembly. And again, looking at this, if you're not familiar with C, can sometimes be a little intimidating to take a look at, but if you're just hunting for these command injections, then one thing you'll get used to looking for is the fact that we have this system that is being called right here. So on line 14, to me, it stands out like a sore thumb here. We have this system call, and this is where this command injection vulnerability is actually now present in here. So looking at line 14 here, we can see that the system call is being made with this string that's passed in this variable __s. So what I'm going to do is right click here, and then we're going to go and rename this variable. So I'm going to call this command_string because this is what's going to be run. Now that we've got the variable named, it's really easy to see exactly where it's used and traced down into this system call. So if we take a look actually at the very top here at line 5, we can see it's being declared as a char pointer, which most likely means this is being used as a string. And then if we actually look down here, we can see there's some memory allocated for it. And then on line 11 here, we see there is a sprintf function that is actually formatting this command string. If you're not familiar with sprintf functions, the way that this works is we pass in a string that we want to be formatted with a formatter inside of it. So here we have this %s, and then whatever is actually passed in param1 here is then going to just be put inside and replaced with this %s. So we actually know then, or have an idea of what param_1 is. So we'll go here and let's rename this variable. And we'll say that this is supposed to be the date_time. So we'll click OK. So it looks like this set system time is actually taking in the date time and then formatting it into this string. So one thing to keep in mind here is that we actually are having this date time that's being passed in by a user be braced by quotation marks, which is a good thing to do because this can prevent command injection, since the interpreter will only actually then treat this as a string, not as potentially any commands. However, the way that this is being done is not proper, because what we can actually do is escape these quotations, since it's not being checked or validated to make sure that our input doesn't have a quotation that we could just escape out of. So we'll take a look then at how to get by this when we are crafting our exploit. The next thing we would usually do now is actually go and trace this and see how it's being called, and take a look at if there is any validation or sanitization that's taking place. So maybe now we would go and reverse engineer that HTTPD. However, since we actually have access to the live system, we can just start poking around there now and see if we are able to get command injection and see it in the logging. Now let's see if we can validate that there is actually command injection through this set system time functionality. So at this point, if you prefer, you can use something like Burp Suite or Kaido or another proxy to do this. However, for the ease of this demonstration, I'm just going to show how we can do it with the built-in developer tools that are in Firefox. So to open those up, go Control-Shift-I, and then I'm interested in the network traffic, so we'll hit network here. And then what I'm going to do is I'm just going to set the system time normally here. So let's set it to, for example, tomorrow. And then we'll pick a time. Let's just go 10:25 a.m. Hit update here, and then we can actually see the network traffic here. So notice there's this get request here to schedule, and then we're passing in a parameter time equals and in this time format. So now what we can do is actually go and just make these requests either with the browser or curl. So again, I'm just going to use the browser itself, and we'll see what happens in the logging now if we put, for example, something that's not a proper time format, and see if that gets picked up. So let's just copy this over here, and we'll go and copy this, and then it was schedule. And we already have that there. And let's just go time. And instead of this, let's actually just pass in maybe something like bad in quotations. And let's hit enter here. And you'll notice nothing happens here in the back end. We see, though, the logging, and we are able to see that what we put in as bad actually gets put right into the quotations here. And then we see there's some errors that system command failed setting time, of course, because it is not a valid time. So For us, this is really good to see. This means there is most likely command injection that we can actually go ahead and exploit. The first thing we'll need to do, though, is figure out how we can get around these quotations, because this, if we don't, is going to block us from having a command to be run. So one way that I'm going to craft this is to use CyberChef, so we can URL encode our command and take a look at how we can then break out of this quotations here. So let's navigate over to CyberChef. So we'll go to cyberchef.io. So what I'm going to do with CyberChef is just use it for URL encoding, so it makes it easier for us to pass in our command injection string right in the URL. So for that, we will just go URL encode. And again, something like Burp Suite or Kaido would make this easier, but just for the simplicity of this demo, I'll show how we can just do it right all in the browser. So we'll bring in URL encode, and then what I like to do is I'll just copy this part of the string. We'll drop it here into our input, and then now we just need to craft our injection string. One thing to keep in mind is we are going to have to escape those quotation bracing that we're having. So what we can do is actually just start with a parameter, so something like bad, and then put our quotation. And then what this is going to do is this will close that first quotation that we have. And then, so it's going to actually then try and set the system time to bad. And then what we can do is actually a common command injection technique of doing ampersand or and, which is then going to tell it to now run a second part of the command, which for us now we can put our injection string. So this could be anything like running an arbitrary command or, reaching out to a command and control server or something like that. I'm just going to do an echo for this demonstration. So we'll go and here, and then we'll go echo, and I'll go the string here that says hello from TCM. And then we'll close this bracket. And then we'll actually make sure we close the other bracket as well. And now down here, we actually have our URL encoded string that we can actually just pass in. So if we copy this here and then open up another tab and then paste this in and then run this, you'll notice we actually get some setting date time, and we get invalid date is bad. And we actually see up here, we get this hello from TCM. So this actually proves to us then that we have command injection because we ran this echo. Again, of course, we could run whatever commands you want, and you should definitely play around with it. For example, we could leak the contents of the shadow file, or write our own script, or there's even netcat already on this. So set up a netcat reverse shell. Again, this just goes to help prove that we actually were able to get command injection. Thanks for sticking around to this point. Hopefully you found this video interesting and helpful, and I would definitely encourage you to go out and hunt for your own command injection vulnerabilities or other vulnerabilities in IoT devices. If you do want to learn more about this subject, then make sure to check out the Beginner's Guide to IoT and Hardware Hacking on the TCM Security Academy. This course goes into a lot more details about how to actually work with real commercial devices and do things like go out and find the firmware online, or actually be able to read it directly off of the device. We also have a certification on IoT hacking in the TCM Security Academy as well, called the Practical IoT Pen Test Associate. So if that's something you're interested in, then definitely go and check that out as well. And there's also a lot of other IoT and hardware hacking resources in our YouTube as well. Again, thanks so much for watching. And if you do go out and hunt for vulnerabilities on your own, please let me know in the comments how you did and if you found any.